Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Hello, everybody. Welcome to our live webinar for Enclustra. My name is Monica Sanchez. I'm the Senior Marketing Specialist for Enclustra. And today, I will be your host for this webinar. Our today topic is fixed point Python code simulation. And this topic was actually brought for us when we were doing our seminars in the US, in the East and the Coast and the West Coast of the US. We actually have these seminars. And the people that attended those seminars, the more than 400 people that attended these webinars, they were actually give us this input of and the feedback of doing and creating these webinars and the topics that they wanted to do. But this time, we are not only having people attending on this webinar from the US. We also have people coming from Armenia, Canada, Switzerland, Germany, Israel, India, the Netherlands, New Zealand, Sweden, Singapore, and Taiwan. Thank you very much for all of you. Thank you for your input, and please keep sending all these inputs. But before we start, I want to share with you and introduce to you this team of people that are actually helping us, our team of the sales team in Enclustra. They are not only here as observers, but they are also helping us in getting all the inputs and all the questions that you may have. Today, we have in backstage, we actually have our head of global account management, Marcus Heinerstegger. We also have Patty Hani, which is our recently appointed senior account manager for the East Coast. We also have Tristan Martin, who is our sales representative from the center and the West Coast of the US. And also we have Vincent Truschler and Emre Demiresen, who are our global account managers. And if you want to contact them directly, you can do it already, but also if you have any questions during this live webinar, remember, this is live, so you can engage with us, sending all your emails and all your questions, and you can actually use it through the live webinar. If you are watching us through StreamYard, please use the live chat that you will have on the right, and you can send us those questions, which we will read to our experts at the end of the presentation. But also, please, if you already have any projects or you have any ideas popping on your head, please send us to these ideas, and our sales representatives, they will be very happy in answer to them. Finally, our expert is going to share a source code today. So if you haven't already, when you register for the StreamYard registration and you requested the source code, we will contact you. Otherwise, you can also send us an email requesting this source code at sales@enclustra.com, and we will be very happy to share that code with you. And now let me introduce to you to our experts. Our expert for today is Dr. Harry Commin. Dr. Harry Commin has studied electronic engineering at the Imperial College of London, receiving a master's degree in 2009 and a PhD in 2013. He then spent 5 years as a consultant, mainly for the UK government. He specialized in algorithm development and FPGA implementation of DSP and digital communication systems. After that, he joined Ericsson in Stockholm, Sweden, to implement high-rate DSP in the digital radio ASICs deployed on their 5G base station. He has been with Enclustra in Zurich since 2019 and is currently our expert lead FPGA SoC engineer at Enclustra. Please join me to welcome Dr. Harry Commin, and once again, thank you very much for being part of this dynamic community. Dr. Harry Commin, welcome to the stage. You are on stage and you can start your presentation. Thank you so much.
Okay, thank you very much and welcome everyone to this presentation, which is all about fixed point numbers and how to use them in FPGA designs. So this is going to be divided into three parts. First of all, we'll look at exactly what fixed point numbers are and why they are so important to us. Then we'll dive a bit deeper into how to design and do calculations with fixed point numbers. And finally, we'll finish off with a complete development flow of a fixed point FPGA component. So why do we care about fixed point numbers? Well, the short answer is that they solve an important problem. And that problem is that neither integers nor floating point numbers give us exactly what we want in a high performance digital system. Because on the one hand, integers are incredibly hardware efficient, so they're fast, they're cheap, low power, low latency, but they have this one really critical flaw, which is that they can only handle whole numbers. And so if we want to do calculations with fractional numbers, then the default option in the software world is to just use floating point. And floats give us fantastic high dynamic range, and of course, this crucial capability to handle fractional numbers. But all of that comes at a high cost, and the cost is that floating point hardware is incredibly expensive. And so really the whole purpose of fixed point is to try to take the best from both of these worlds. So we want to take the hardware efficiency from integers and sort of add on this capability to handle fractional numbers, a little bit like how floating point does. But of course, in all of engineering, we very rarely get anything for free. So of course, in reality, this is actually a trade-off. And the trade-off here is that fixed point numbers are significantly more difficult to use. And so they require the developer to have a higher skill level. And so in this first section, we're just going to break down these points and make sure we understand exactly how fixed point numbers work and what their similarities and differences are with integers and floating point numbers. So we're all familiar with integers. If I were to ask you to write down what year it is, you could immediately write down 2023, and we all know how to interpret this number because these digits are weighted with increasing powers of 10 from right to left. And similarly, if we want to write the year in base 2, it might take a little more conscious effort, but essentially all of the same rules apply here, and these binary digits are weighted with increasing powers of 2 from right to left. And so we can write 2023 like this. But what now if we want to represent a fractional number like 2023.1? Well, not much has actually changed here. We've added one extra column to the right with the next smaller power of 10, so that's 10 to the minus 1. And we've added this decimal point here that just indicates to us where the integer part of this number ends and where the fractional part of the number begins. So it should be pretty easy to now write that number in binary, right? Well, actually, we have a bit of a new problem here, which is that to write that number in binary, we would need an infinite number of bits. And the reason for that is that the binary expansion of 0.1 is an infinite recurrence. And so we can never exactly write that number in binary. We can get closer and closer as we add more and more bits, but we can never quite get there. So what do we do if we want to write 2023.1 in a practical digital system? In reality, we basically just don't. We instead approximate it with some finite number of bits, and we just accept that there will always be some inevitable amount of rounding error. And that can lead to some surprising results because, for example, both of these equations here should clearly evaluate to exactly 0. But in any practical digital system, we are very likely to get non-zero results here due to rounding errors. And so as humans, it can be very tempting to look at these results and say, wow, our computer is so stupid because it can't do basic arithmetic correctly. But really, I think it's important to note here that actually we humans are equally to blame for this situation. Because we've all learned to count on 10 fingers, we naturally feel that base 10 is somehow more intuitive. But really, we have no right whatsoever to assume that base 10 is somehow mathematically special. And so, especially when we are dealing with fractional numbers in a practical digital system, it's important to always be very mindful of this fact that compact decimal numbers are not necessarily going to behave well in a binary system. And I think a nice way to expose our ingrained human dependency on base 10 is with this well-known mathematical joke. And we read this as, there are 10 types of people in the world, those who understand binary and those who don't. And of course, this joke only works because we automatically read this sentence in base 10, whereas it actually only makes sense in base 2. So I think now we need to say something more concrete about exactly how we represent fractional numbers in a practical binary system. Because up until now, we've just sort of assumed that this binary point exists somehow, but it's not made of ones or zeros. So how do we actually represent that binary point in digital logic? And actually, the answer to that question really takes us directly to the heart of what is the difference between a fixed point number and a floating point number. Because on the one hand, in fixed point, that binary point is actually not represented anywhere in hardware. And arguably, it only truly exists inside the mind of the developer. And what that means is that at design time, the developer has to decide where this imaginary binary point exists, and then it stays fixed in that location forever afterwards. Whereas on the other hand, in floating point, the location of that binary point is explicitly encoded in an exponent, which is part of the floating point number. And so that consumes some real bits, but we can modify those bits at runtime. So that means we can move this binary point, or it can float dynamically. So here's a quick example of a fixed point number. And we're imagining here that our developer once again wants to try to represent 2023.1. And so they've decided that to represent that number, they need 11 integer bits to give them enough dynamic range. And let's say for the sake of this example that 5 fractional bits will give them sufficient precision for their application. And so that gives us this number on the right, 2023.09375. So just to summarize what we did there, we have 11 integer bits plus 5 fractional bits, no sign bit because this is an unsigned number. And so in total, that gives us a 16-bit fixed point number. And at Enclustra, we like to express the format of our fixed point numbers using these 3 pieces of information. So we have the number of sign bits S, which must be 0 or 1, the number of integer bits I, and the number of fractional bits F. And so in this example here, we would express this fixed point number format as 0, 11, 5. And many, many other notational conventions exist for expressing fixed point number formats, but essentially they all must boil down to exactly the same thing because they must all be able to express these 3 fundamental pieces of information. So moving on to a floating point example, what we have here is a half precision float. So this is a 16-bit floating point number. And once again, we're going to try to represent the number 2023.1. And the details of exactly how this exponent is encoded and how the mantissa are encoded are not really important for now, but the end result is that the best we can do in this case is 2023.0. And so you may have noticed that the rounding error with this floating point number is significantly worse than with the fixed point number. But actually that is a completely expected result because we've invested 5 out of our 16 bits into this exponent. And that exponent gives us more dynamic range, but then that leaves fewer bits available for representing contiguous precision. And so in general, floating point numbers have less contiguous precision than either a fixed point number or an integer. So I'll just say something very quickly about negative numbers because actually the situation in fixed point is exactly the same as with integers, which is that we almost always use 2's complement. Several other options exist. I've written 3 of them there, and each of those has their own niche. but in the vast majority of cases, we use 2's complement. And just in case you're not familiar, the trick with 2's complement is simply that the most significant bit carries a negated weight. And so it's still a power of 2, but it has a minus sign. And that just allows us to represent negative signed numbers in fixed point. So next, I think it's important to clarify exactly how we represent very small and very large numbers in fixed point, because this is often a cause for confusion. But just the one key point that you really need to take away from this slide is simply that the binary point does not need to be within the represented bits. So for example, if we want to represent a small number like 0.01 in 8-bit fixed point, then we can choose an 8-bit range that is quite deep into the negative powers of 2 and not up near the binary point at all. And so in this example here, we would say we have -6 integer bits plus 14 fractional bits, which overall gives us an 8-bit number, which is suitable for representing small numbers around 0.01. And then similarly, if we want to represent a much larger number, like 10,000 in 8-bit fixed point, then now we can select a bit range that is much deeper into the positive powers of 2. So in this example here, we would say we have 15 integer bits minus 7 fractional bits, which overall gives us an 8-bit number suitable for representing large numbers around 10,000. But just to be absolutely clear here, when we're talking about fixed point, we should really be saying very small or very large numbers. Because of course, with floating point, we really could have both of those options simultaneously, whereas with fixed point, we really have to choose one format at design time and then stick with that forever. So I've left the most important point to last here, which is the hardware cost of floating point operations. Because that little exponent may not seem like a very big deal, but it turns out to be very, very expensive to handle it in hardware. And the reason for that is that, for example, if we want to add together 2 floating point numbers, then we first need to implement dynamic bit shifting to align the binary points before we can then integer add the fraction parts. And it turns out that dynamic shifting is very expensive in hardware. Or similarly, if we want to multiply 2 floating point numbers, then again, we have to explicitly handle the exponent part before we then multiply the fraction parts. So it's more expensive. And in this table at the bottom here, I'm just summarizing some relative costs of doing multiply add operations in an FPGA. But really the whole message to take away from this table is that in the vast majority of cases, floating point is just unusably expensive, because particularly if we're looking at investing many hundreds of lookup tables to do a single multiply add compared to potentially 0 in the fixed point case, then I hope it's clear to see that if we use floating point, then we are very quickly going to congest and fill up our FPGA device. And so we really need to start here with the mindset that floating point is not an option, except in very unusual niche cases. Okay, so hopefully now we have a pretty clear overview of what fixed point numbers are. And so now we'll look at how to design and make algorithms with them. So in my opinion, the key challenge here is all about controlling bit widths, because every single arithmetic operation that we do will tend to increase the width of our signal. And we cannot just allow that to continue forever, because, for example, in this diagram here, what we can see is we have a few 16-bit input signals, and then we just do a handful of multiply and add operations. And if we really keep full precision through all of those operations, then suddenly our output has ballooned to 115 bits. And so then to do anything with such a wide signal after that is going to be incredibly expensive. And so the task of the developer here is to really analyze at every single node in their design, how many bits do I really need? How many integer bits do I need for dynamic range? How many fractional bits do I need to give me enough precision to meet the performance requirements of my system? And to answer that question, we're going to look at a few things now. So first of all, we're going to look at, well, what actually is the worst case in terms of full precision when we do these types of operations. Then we'll look at what options are available to then reduce those bit widths from full precision to something more manageable. And finally, we'll go through several design examples. So how many bits do we need to represent the result of some arithmetic operation? How many integer bits will it need? How many fractional bits will it need? And will this result need to be a signed number or an unsigned number? Well, my simple advice here is to just use a fixed point math library, because it can be surprisingly tricky to calculate all of these worst cases for all of these fixed point operations. And also, quite frankly, it's just very tedious. I mean, when we're in the middle of developing our algorithm, we probably don't want to be stopping constantly to try and figure out what the worst case might be for doing an addition, for example. And so at Enclustra, we've written our own fixed point math library called ENCLFix. It's free and open source, so you're free to download and use that if you would like to. But if you're already using some other tool like MATLAB's fixed point designer toolbox, then that's a great tool for doing your software modeling. Or on the HDL side, if you're using something like VHDL 2008's fix package, then that also works very well. So by all means, use those tools if you're already familiar with them. At Enclustra, we slightly prefer our own library, and one of the main reasons for that is simply that all of these function calls look the same in Python and in MATLAB and in VHDL and in any other languages that we might want to add support for in the future. And another reason for us is that not all of our customers will necessarily have MATLAB licenses, and so it's just good for us to have that free Python option available as well. But I would just urge you, whichever path you choose to go down, I would urge you to choose a good fixed point math library and use it, because it really does make all of fixed point development much easier and much, much less error prone. So now we're just going to go through one of these output format calculation functions as an example, because like I said, this is pretty tedious, and most of the time it's something we just want our math library to take care of for us. So what we're going to look at here is how much bit growth occurs in an addition operation. And so we probably all know that in integer arithmetic, we always need to add one bit to the output of an addition in order to guarantee that we can represent the result without numerical overflow. And in fixed point, the situation is pretty similar in that we usually need to add one extra integer bit. But there's quite an interesting edge case here that I think is worth mentioning, which is that if we add together two fixed point numbers with non-overlapping bit ranges, then that can actually never overflow. So for example, if we want to add an 8-bit integer to an 8-bit purely fractional number, then the result of that addition can never overflow. And what that means is that the result of this calculation should be a 16-bit number and not a 17-bit number. But really, this is just one of those small details that we want our fixed point math library to take care of for us. We don't want to have to stop and think about these small details all the time. Okay, so moving on now to look at what options are available for reducing the bit width of our signal. And the first option we're looking at here is to consider discarding some of our most significant bits. So of course, the risk we run when we do that is that we could cause a numerical overflow if we discard a bit that was actually being used. And so in this graph here, I'm showing a classic example of a numerical overflow, because what we have here is a sine wave that reaches all the way up to 1.0, but we've just thrown away the integer bit that we need to represent that 1.0. And so as a result, what we get is this very ugly wraparound all the way to -1. And in most contexts, that represents a really bad numerical error. So what do we do in a situation like this? Well, I'm going to suggest 4 things that a developer might like to consider in a situation like this. And to do that, I'm just going to zoom in on this top region of the sine wave, because that's where all the interesting stuff is happening. And so the first option here, I would say, would be maybe we need to consider not discarding that particular integer bit. I mean, if we really need to represent 1.0 in this system, then maybe we just need to invest that extra 1 bit here, and maybe we'll look somewhere else to save some bits later. The second option here is to just implement saturation. The first downside of saturation is that we have to invest a little bit of logic in order to implement that. And the second downside is we have actually distorted this signal because we've chopped the top off it. And in some contexts, that little distortion could be absolutely catastrophic, and in other contexts, it may be completely fine. And so it's up to the developer here to analyze this and decide whether saturation may be a viable option. And the third option here could be to consider downscaling the signal somewhere upstream. This really depends on where the signal is coming from. But for example, in some cases, it could be possible to maybe decrease the gain in a previous component just enough so that we can guarantee that the signal arriving into this node will always come within the representable range of this number. But of course, in many cases, that option just won't be available. And in some other cases, maybe it's undesirable because maybe we don't want to distort the magnitude of our signal in this way. So again, it's up to the developer to analyze that and decide. And the final option here is to maybe consider just allowing the overflow to happen. Now, this is pretty unusual because in most scenarios, an integer overflow is a really big problem that we want to avoid. But if the developer can completely justify that this is totally fine in their system, well, then they shouldn't invest effort or FPGA resources in any of the other three options. Okay, so now, of course, the second option we have for reducing the bit width of our signal is to consider discarding some of the least significant bits. So here we're talking about throwing away some of our precision. So we need to think here about rounding algorithms. And this table here is a bit of an oversimplification, but I'm going to say that roughly speaking, there are these three rounding modes that will cover us for most of our everyday use cases. So the first algorithm here isn't really much of an algorithm at all. It's just crude truncation. And of course, the good thing about truncation is it costs literally nothing. However, the rounding errors are very large and they are all biased heavily towards negative infinity. So then the second algorithm we have here is this familiar round to nearest algorithm, which has a pretty low resource cost, and it has minimal error because it will always round to the nearest valid number. But when it's exactly halfway between two valid options, then it will always round upwards towards positive infinity. And so what that means is that this rounding algorithm does have a statistical bias. So if you happen to be implementing something that is sensitive to statistical bias, then you need to go for this third option, which is convergent rounding. And convergent rounding, again, has minimal error because it always rounds to the nearest valid number. But when it's exactly halfway between two valid options, it will always round to the nearest, let's say, even number. And so the end result is that half of our ties will end up getting rounded down to an even number. The other half get rounded up to an even number. And so the net result is we have an unbiased rounding algorithm with minimal error. But of course, this option carries the highest resource cost. And there's one more point here that I think is really important to think about, which is, can the rounding algorithm itself cause an overflow? Because, for example, if we want to round a number like 255.75 to the nearest integer, then 2 out of 3 of these algorithms are going to round up to 256. And so if we're not very careful, we are going to have an integer overflow on our hands here, which could be a really big problem. But once again, this is really just one of those things that we want our fixed point math library to take care of for us. We want the library to tell us what a safe format is for representing the result of this operation. And so for that reason, in many ways, we have to treat rounding a little bit like all of our other arithmetic operations. And so we just add it onto our list in our library, and we let the library take care of the details. Okay, so moving on now to our first design example. And what we want to design here is a simple accumulator. And we want to add together 100 numbers. And the design question is, what do we need to do to prevent the output of this accumulator from overflowing? So we saw earlier in the presentation that each addition operation typically needs 1 extra bit at its output in order to prevent overflow. And so to add 100 numbers together, we have 99 adders, and so the output's going to need 99 more bits, right? Well, actually, that's completely wrong. And the mistake that we've made here is that we have zoomed in far too much on the individual worst cases of these separate additions. And really what we need to do here is just take a bit of a step back and look at the accumulator as a whole and consider the worst case for that. And I think it should be pretty easy to see then that actually the biggest possible output value from this accumulator is simply going to be 100 times the biggest possible input value. And so in the vast majority of cases, when we analyze that properly, we find we only need 7 bits of growth and certainly not 99. So our second design example here, we want to design an RGB to grayscale converter. So this is a really common component in the world of vision systems that we use to convert a color image into a grayscale image. And actually the architecture of this thing is very similar to the accumulator that we just looked at, except now we're only adding together 3 numbers instead of 100, and we are slightly scaling down each number before the addition. So I think it's pretty easy to see here that the maximum possible output value in this case is going to be 0.299 plus 0.587 plus 0.114 times the maximum input value. And it just so happens that all of those numbers add up to exactly 1. So what we have is that the maximum output value is exactly equal to the maximum input value. And so we don't need any extra integer bits on the output. Or do we? Because in fact, we may have just fallen into our own trap, because we said at the start of this presentation that we need to be very mindful of assuming that decimal numbers are going to behave nicely in a binary system. And so our assumption here that these 3 decimal numbers are going to add up to exactly 1 could be a very dangerous assumption. And so we need to properly check this calculation in fixed point. And when we do that, what we find here is we have an absolute minefield. And if we're not being careful, we're just basically playing Russian roulette, because sure, many of these fixed point formats will give us a weight sum of exactly 1. But actually, there are some cases here that sum to a little bit more than 1. And so in those cases, under certain conditions, we could get a numerical overflow, which would be a really big problem. And so I'm just showing a few examples of that here, where the 2 images on the left have had no overflow, so they look okay, but the 2 images on the right have had an overflow. So there are some white regions of this cat that are appearing as black. And I think a really important point to make here is that when we think about rounding errors, we will naturally tend to think that the solution is just to increase precision. But it is not that simple in this case. Because, for example, just going from this image to this image, all we did was increase the weight precision, and that has caused an overflow to happen. Or maybe even more surprisingly, going from this image to this image, all we did was increase the pixel precision, and that has caused an overflow. But just to be clear, of course, also decreasing precision can be a problem. So the point I want to make here is we shouldn't just assume that some action will solve the problem. We really need to understand the problem and apply the correct fix. And the correct fix here is to properly calculate the worst case and design for that worst case. Okay, so the final design example here, we're looking at an FIR filter from the world of digital signal processing. And actually the architecture here is almost identical to the previous example, except now instead of just adding 3 numbers together, we're going to add together some arbitrary number k. And the second really important difference in this case is that now we have signed numbers. So the input data x is signed, and the filter coefficients h are also signed. So let's imagine we speak to our DSP expert and they say, here are your filter coefficients. Please make sure the output of this filter can never overflow. So how do we go about solving that problem? Well, our first idea might be to just do the same as we did in the last 2 examples and simply input the biggest possible input value we can and see what comes out on the output. But actually that's a big mistake, because when we do this, sure, this will produce big contributions in alignment with the positive filter coefficients. But actually, when this aligns with the negative filter coefficients, that's going to subtract from our output and make it smaller. So it turns out that actually the worst thing we can possibly input looks like this. And so what we're doing here is in alignment with the positive filter coefficients, we are driving the input with the maximum positive value, whereas in alignment with the negative filter coefficients, we're driving the input with the maximum negative value. And so I hope it's clear then that all of those contributions will then add up positively towards overflowing our filter output. And so when we input this absolute worst signal into our filter, and when it aligns in the worst possible way with the coefficients, what we see is that the maximum possible output value from our filter is about 1.6. And so the answer to our design question here is that we need one extra integer bit on the output of this filter to guarantee it will not overflow. Okay, so now it's time to move on to looking at a complete development flow for a fixed point FPGA component. So we're going to go all the way from designing and analyzing the component in software through to implementing it in HDL and finally verifying it and testing it. Just a quick disclaimer here. In this section, I'm going to describe how we like to do fixed point development at Enclustra. Of course, this is not the only way to do it. This is just the way that has evolved for us through many years of doing many fixed point projects with FPGAs. So really, my only hope from this section is really just that hopefully there'll be enough interesting points for you that you might be able to find one or two things that you could take advantage of in your own development. So what are we going to develop now? Well, actually, we're just going to reuse the last design example that we looked at. So we are going to develop an FIR filter with filter coefficients that look something like this graph on the right. So before we jump into developing our component, I just want to explain what we're about to do, so hopefully we won't get too lost along the way. So the first thing to mention here is that our whole development flow is built around what we call a bit-true model. So that is a pure software model written in Python. That's not for synthesis. It's just purely for modeling the exact fixed point behavior of our component that will eventually operate in the FPGA. And so the first development phase is the design phase. And this is where we write our bit-true model and we use it to analyze the performance of our FIR filter. So this is where we tweak our fixed point number formats until we get some acceptable performance to meet the requirements of our project. And then the second development phase is just normal RTL implementation. And the third phase is verification. So in this phase, once again, we use our bit-true Python model, this time for doing what we call co-simulation. So that means we have this co-simulation script in Python, which generates a very large amount of input data. It pushes that data through the bit-true model in order to generate the expected output that we expect to see later in the RTL component. And then it saves all of that data into these co-simulation data files at the bottom. So then all that the HDL test bench needs to do is load up all of that co-simulation data, push the same input data now into the RTL component, and then simply on the output side, just check that every output that comes from the RTL component perfectly matches the output that we saved from our bit-true model. And we don't really have time to talk about hardware testing today, but essentially it works exactly the same as verification, except now we push our co-simulation data through the real design running on hardware instead of a simulation. Okay, so the first thing that we need to do is to write our bit-true Python model. So how difficult is this? Well, in most cases, and including this case, it is very simple. And it is made simple because we've understood from earlier in this presentation how to keep control of our bit widths and how to do some internal calculations at full precision and then apply rounding and saturation to reduce our bit widths to make them more manageable. And so what that means for our FIR filter is that all of the numerical processing that we need to do in this fixed point model is contained within just 2 lines of Python code. And so in the first line, we just use a standard off-the-shelf Python library function to do the FIR filtering in floating point at full precision. And then in the second line, we actually apply the fixed point rounding and saturation. And we're using one of our enclfix library functions to do that. So of course, we wrap up these two lines of code in a Python class, and we add some bells and whistles to make it easier to use. But really, all of the numerical processing is contained within just those two lines. Okay, so now that we have our bit true model, we can now use it to design our FIR filter component. So of course, there are many, many types of analysis that we may want to do on an FIR filter like this. But this presentation is not about DSP theory. So for now, we're just going to assume that we want to evaluate the step response of this filter. So in this graph here, what we're doing is we're inputting this square step function into our bit true model. And then we are comparing the output from the bit true model with an ideal floating point reference. And let's say that here we look at this error and we say that this is not acceptable. This is too large. It does not meet the performance requirements for our project. And so what do? Well, we go back to our design and we reevaluate our fixed point number formats, and we tweak them a bit. We give them a little more precision until the error is reduced down to a level that we can say, yes, this is acceptable. This meets our requirements, so we can move on. And just another example here, we could, for example, have some kind of frequency domain requirement for our filter. Like maybe, for example, we require the stop band attenuation to be at least 50 decibels. So once again, we can do some analysis, draw some graphs, and we find that we're not quite meeting our requirement here because this stop band response for the fixed point case is just slightly creeping above negative 50 decibels. And so once again, what we do is we go back to our design, we tweak our fixed point formats, give ourselves some more precision until the error falls down to an acceptable level for our project. But really the whole point I want to make here is regardless of whatever type of analysis we're doing here, it's going to be easier to do it in software. Because in software, we have all of the great analysis tools we want, like graph plotting and fast Fourier transforms, and we can dump data in and out of files very easily. And so just by writing that little fixed point model, we've got access to very powerful analysis techniques. Okay, so moving forward now to the RTL implementation, this is where now we really need to take care of all the non-numerical aspects of our implementation. For example, things like pipelining. Of course, the bit true model doesn't care at all about pipelining, but in our RTL implementation, we are certainly going to want to implement proper pipelining in order to achieve a reasonable clock frequency in our design. And similarly, there are plenty of other things we might want to do in this phase. For example, little resource optimizations. So in this example here, our developer has noticed that they can implement rounding completely for free because the top adder in the left-hand figure is not actually using that adder. We're just carrying in a 0. And so they notice that if instead of carrying in 0, we carry in a half, then we get rounding completely for free. But the point I want to make here is that this optimization has changed the RTL, but actually numerically from the outside, nothing has changed at all. And so the fixed point model has not had to change. And actually, we can take these optimizations much, much further because, for example, we said earlier that we want this filter to handle filter coefficients that look something like this graph in the top left. And it turns out that those coefficients are symmetric about their center. And what that means is we can actually completely rewrite and restructure the internal architecture of our FIR filter on the right in order to exploit that special symmetry in those filter coefficients. And the details of this rearrangement are not really important, but the point that I want to make is that now this final architecture on the right is barely recognizable from the architecture we started with when we were thinking about the bit true model. But numerically, it's still identical. So we didn't need to update the bit true model at all when we did all of these complicated optimizations. And just to finally enforce this point, I think a really great example of this is the PSI fix library. So PSI are the Paul Scherrer Institute, who are a research institute in Switzerland, who do particle physics, among other things. So in their particle accelerator, they do a lot of digital signal processing. And so they have this free open source DSP library called PSIFix, which is built on top of Enclustra's ENCLFix library. But in PSIFix, there are 5 FIR filter implementations. And internally, they are all heavily optimized for very different use cases. They have very diverse and different architectures, but they all still share a single bit true model. So once again, the point I want to make here is that the RTL may be very, very complicated, may have very diverse architectures, but usually the bit true model side is really very simple indeed. And so it's a very small investment of effort to get this bit true model that pays us back in so many ways in our development flow. Okay, so coming back to our own design, there's not too much to say about the HDL implementation. In terms of arithmetic, there are only 3 operations that we do in the VHDL. We pre-add, and then we multiply, and then we post-add. And we use our ENCLFix function to do those arithmetic operations in VHDL. And maybe it's just worth mentioning what exactly we input to these functions. So we input both of the input data values along with their fixed point number formats. And also we have to specify the format of the result of this operation that we want to be output. Okay, so we have written our bit true model. We have written our HDL implementation. And so now we need to next think about how to verify the HDL implementation. So what we need to do now is write our co-simulation script. And the task of the co-simulation script is to generate a very large amount of input data, push that data through the bit true Python model, and then save all of that output data to files, because that's what we want to use later to verify the output of the RTL component. And of course, we can repeat this whole co-simulation procedure with many, many, many different parameter combinations. So in this example at the bottom here, I've just defined 144 parameter combinations where we're modifying the input bit widths, the output bit widths, and also the filter configurations in terms of the cutoff frequencies and the numbers of taps. But of course, if we need to increase this to many thousands or tens of thousands of combinations covering all kinds of different parameters, then of course that is a very, very easy thing to do in Python. Okay, so our HDL test bench actually is quite simple in this case because all it needs to do is read up all of that input data and configuration data that the cosim script saved. And then it needs to load in that input data, push it into the RTL component. And on the output side, all it needs to do is check sample by sample, does every single output from the RTL component perfectly match the output that we saved from the bit true model. And so when we run this simulation, of course, we can do all of the usual things like waveform debugging. And I've just got a simple screenshot here where we're looking at the input to our FIR filter and the output coming out of it. And it may be a little difficult to see, but you might be able to recognize one or two things here. Because first of all, on the left here, we are inputting a step function and measuring the step response. And of course, the output that we now get in our HDL simulation is identical to the output that we got earlier when we used the bit true model. And also over on the right here, you may be able to recognize that we are testing the absolute worst case overshoot from our filter. And once again, the output from the HDL simulation is producing identical results to the bit true model. So of course, once our HDL implementation is relatively stable, we don't want to be staring at wave windows for hours just to verify that it's working. So of course, we want all of our test benches to be fully automated and self-checking. And at Enclustra, we like to use the vUnit verification framework for doing that. And so in our case, to run these 144 test cases, we would just execute this run.py script in Python like this. And then we would allow vUnit to take care of running all of the test cases. And when that's finished running, it will print out a little summary like this that just tells us that all of our 144 test cases have passed. And there's maybe just one small detail here that is worth mentioning that's a little bit special about our run.py, which is that we pass our co-simulation script as a callback function. And what that means is simply that each time we run this simulation suite, it will automatically take care of regenerating the co-simulation data, just so we know that that data is fresh and up to date. And finally here, I just wanted to show an example of what happens if we do introduce a bug into our system. So what I did here was I deliberately broke the bit tree model. So I changed the rounding mode in the bit tree model to convergent rounding. So now the bit tree model is doing convergent rounding, whereas the RTL is still doing ordinary half-up rounding. And what that means is that in some rare cases, the least significant bit may be different between those two implementations. So that would be very difficult to detect by eye, but of course, an automatic test bench detects it, no problem. And so 59 of our test cases have failed. And so it's very immediately apparent to us that something is wrong and we need to step in and do some debugging. And actually, that's all we have time for today. So a couple of next steps for you. First of all of the source code from this presentation is available. So please get in touch and we'll send that to you. Secondly, I already mentioned the ENCL fix library. It's free and it's open source. So please, if you're interested, try that one out. And of course, don't hesitate to contact us, particularly with this presentation. Because we're providing the source code afterwards, I fully understand that there will be technical questions that come afterwards. So please send those technical questions direct to me. And for any general inquiries, sales@Enclustra. And just finally, our design services. Of course, if you have any kind of an FPGA project that you would like help with in any capacity, then please reach out to us. We would be delighted to help you. And thank you very much for your attention. I'd be happy to take any questions now.
Thank you very much, Dr. Harry Commin. It's very insightful what you have presented. And yes, we have actually some questions coming in beforehand, also from the StreamYard, but also we have a couple of questions that we have on the live chat. So I would like to read this to you. And Dr. Harry Commin, can we contact you directly if we have questions? You already provided your email.
Yeah, absolutely. So any technical question related to the presentation itself, or in particular the source code that comes afterwards, please reach out to me directly with that. Or also actually any feedback about the topics that were presented today, because I tried very hard to include all the topics that people expressed interest in at the previous events, but I'm absolutely certain that I've missed some important things because 45 minutes is very, very short. So if you are really hoping to hear about something today, which I failed to present, then please reach out to me and let me know, and we'll try and squeeze it into a future event.
Excellent. Then we have, can we contribute to the fixed point library in GitHub?
Yeah, absolutely. We would be delighted to have contributions to ENCL fix. We are fully aware that there are lots of things that we really would like to improve, particularly on the Python side. So yeah, please open issues, send emails to me. We would be very happy.
I'm most interested in the practical use of the ENCL fix library and how to quickly build expertise in using it.
Right, so to be honest, I would say that probably the best starting point for that now is actually the source code that we are providing with this presentation. Because I wrote all of that source code from scratch just to try to give a clear and easy example for a beginner to get started with it. If you're looking for some more advanced examples, then the PSI fix library that I mentioned in the presentation would be a good option for that. So if you Google PSI fix, then you can find they have a very large library of DSP components that are all using ENCL fix. So that'll give you lots of examples to learn from.
Great. Fixed point implementation on FPGA using VHDL 2008.
Right, yeah, so I only touched very briefly on the HDL 2008's fix package during the presentation. Like I said, it's a good tool. We have used it in our own projects. and we didn't have any major problems with it. We slightly prefer using our own library, but the fixed package is a perfectly good option. And honestly, it's largely compatible with ENCL Fix. They both offer a lot of the same functionality.
Next question I have, can your library infer Xilinx DSP slices?
Right, so the answer is mostly yes. So we can successfully infer all of the main parts. So we can infer the pre-adder, the multiplier, and the post-adder. What we can't yet infer out of the box that we would like to add support for are the features of the pattern checker. So in DSP48E, it should be possible to implement either saturation or convergent rounding using the pattern checker, but currently that does not infer out of the box. And so that's something we'd like to add in the future. But apart from that, yes, inference works.
And from the live chat, we have this question: how soon will system Verilog be added to the ENCL Fix suite?
Right, so the honest answer is it will depend on demand, and we are starting to hear more and more demand for Verilog and system Verilog. And so please keep sending us that feedback that you want it, and we will do it, because we want it too. We just need a push to do it.
The next question that we have on the live chat is, have you tried passing your bit through Python model through Python-based HLS, such as Mayan or Amaranth? The idea is to skip the manual translation to HDL steps altogether.
We have not tried that. I think in general, our experience with HLS is that it tends to overpromise and underdeliver. And so we feel very capable with an ordinary HDL, but certainly if we see a really great HLS option that could do that, then we would certainly use it. But currently, no, we don't do that.
Okay, we have another question. How are the tau blocks different from the delay set -1 block in the figure in your slide number 40?
Right, good question. So there is a difference between a sample delay and a cycle delay. So a z to the -1 is a sample delay. So that exists in the mathematics. And that's a delay line in an FIR filter produces sample delays. But when we do pipelining, we are just doing clock cycle delays. And so a pipeline delay will always register, whereas a sample delay only registers on valid data. So there is a subtle difference there, but it's a very, very important one.
Another question that we have, will your Commin also work with GHDL or even Verilog only very later for simulator, both being open source, contrary to modulism?
Yeah, so we use GHDL with VUnit. I haven't tested the code from this presentation with GHDL, but it is largely compatible with VUnit, so it should work. Regarding Verilator, no, I haven't tested this with a Verilog simulator.
Next question we have is, what is the main advantage of using the Enclustra fixed package over a standard fixed OU fixed?
Yeah, so that again is the VHDL 2008 fixed package. For us, the advantage is we like the consistent syntax between our VHDL and our Python and our MATLAB. The other small detail that bothers us a little bit about the VHDL standard implementation is that it has separate types for signed and unsigned, which makes it more difficult to make generic components that can handle either signed or unsigned. And so having a 3-part format that just allows signed, unsigned, any integer bits, any fractional bits, for us, we find a little more flexible. But honestly, if you like fixed package, then I would say use it. You know, there's nothing wrong with it.
Any plans to support Verilog in the ENCLF fixed library? Please, is is an example of code simulation workflow, including make scripts part of the GitHub repository?
Okay, so I think there were two separate questions there. The first one was,
Yes.
do we plan to support Verilog? Yes, absolutely we do. And we are lighting a fire under it because we are getting this feedback that people are interested in it. So I'm hopeful that that's going to happen in the coming couple of months, especially as people keep telling us that they want to see it. So yes, we are going to do that. Then I think the second question there was, is an example of co-simulation workflow part of the GitHub repository? Right, so the GitHub repository of ENCL Fix currently is not in the best state because we have a very large amount of development sitting in a feature branch waiting to get merged back to the main branch. And so in the feature branch, we have some good simulations for that, but we are blocked in merging that back to main at the moment because we're having trouble open sourcing one of the dependencies there. So we're working on that. But the code that we are providing with this presentation does include everything you need to do that. So yeah, contact us for the code here and it will do that.
And two last questions. Does your Python library include floating point to fixed point and fixed point to floating point conversions functions in order to easily generate fixed point values for the FPGA design, for example?
Yes, yes, it does. Yeah, that's one of the standard library functions, yeah.
Okay, and the last one that we have here on the live chat is, does the resize function in the IEEE fixed point package, VHDL 2008, uses convergent rounding?
It can. So I can't remember off the top of my head which rounding modes are supported, but I'm almost 100% confident that convergent rounding is one of the supported modes. You have to either configure it via a package generic, I think, or when you make function calls, but I'm pretty certain convergent rounding is included.
Those are all the questions that we have in this moment, but remember, if you want to send more questions and you have any other concerns or projects that you may have, please contact Dr. Harry Commin directly for the technical questions, or if you have any consultant, please sales@enclustra.com. This is all. Thank you very much, Dr. Harry Commin. It was very insightful. And everybody, please stay in touch. If you haven't just yet, follow us on LinkedIn, follow us on YouTube, and also on X. We will be very happy in receiving your feedback so we can create more of these webinars. And so if you don't have any more questions, then we can leave it here. And until the very next time. Thank you so much and see you soon.
Embed has never been so exciting. It's life-saving. It's life-changing. Dream making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.